Okay, great. So this second invited talk of the session. So we have András Gilyén from the Rényi Institute of Mathematics, who's going to talk about quantum generalizations of Glauber and Metropolis. Thank you.
So first of all, which microphone do you prefer, this one or the other one? I don't know if in the back you can hear me well. Can you hear me well in the back? Not really. Then I would prefer the other microphone. Or at least, yeah, for the sake of the audience.
This one.
How about this one? Okay, good. Okay, so I'm going to talk about quantum generalizations of Glauber and Metropolis dynamics. And it might sound a bit distant for some people who come from more experimental background. But what's really the goal? The elephant in the room is that we have heard lots of improvements and room for improvements for dynamic simulations of quantum systems. But to do some interesting with simulation, you need interesting starting state to begin with. And there was lesser attention to this problem in the talk so far, and also in the literature somewhat. And we don't really have a very reliable go-to algorithm when you want to prepare a low-energy thermal or ground state. And it has been pointed out in literature. A notable example is Garnet Chen and company discussed how problems where classical simulation methods break down are the problems also where common quantum methods for preparing initial states, such as adiabatic algorithms or variational quantum algorithms, seem to break down. So if the problems where classical simulations break down, also the problems where quantum state preparation breaks down, then we are not helped that much by a quantum computer. So we explored, motivated by this, we explored alternative methods for doing state preparation, in particular Gibbs states, and that covers also ground states. And Anthony Chen is going to speak after the break also about this problem, and I am going to take a bit more theoretical look at this family of algorithms that are related to Gibbs sampling. Okay, so I'm going to start with the classical versions of these algorithms that are known on the names of Metropolis and Glauber dynamics. So what's the goal? The goal, we want to sample, in the classical case, from a probability distribution, a target distribution. And for this, we know a vector, a large dimensional vector with some entries, but it doesn't have to be normalized. So think about Gibbs sampling to motivate this problem. For example, I have an n-spin Ising model where the spins can be plus or minus, and I have n of them. And this classical Hamiltonian could be just, for example, a nearest neighbor model when I have some weight for nearest neighbor pairs and some field. And in this case, I would like to sample a configuration whose probability is proportional to the exponential of the energy, and beta is this inverse temperature parameter. And even if I have a few spins, the configuration space is 2 to the n, so exponentially large, and it's hard to account for all the configurations, and in particular, it's very hard to know the normalization. It's a very difficult computer science problem to compute that quantity, actually. So it's a challenging task to sample from this distribution that is proportional to this exponential. But there are some nice methods that people propose for this. And so this goes as follows. Take some symmetric exploratory Markov chain on this large exponential dimensional space. And the very easy such procedure is just pick a random spin and flip it. That's a very easy procedure. Unfortunately, it doesn't sample from this distribution. But we can modify it, and this is the Metropolis algorithm. And it says that, okay, look at the transition. Suppose that your Markov chain would tell you that, okay, let's make transition from configuration Z to Z prime. Then the rule is the following. if the likelihood of this configuration increases, so your the configuration Z prime is more likely than the configuration Z, then you just accept this move, then you are happy, you move to a more likely position. However, if you move to a less favorable position, then you should reject this move with some probability, and this turns out to be, or in other words, accept this move only with probability, this likelihood of Z prime divided by Z, configuration Z prime over Z. And this is the Metropolis algorithm, and there's also Glauber dynamics, which is also in the ballpark of these algorithms, and it just says that, well, you don't always accept moves that are increasing probability, but also reject them with some, and it's kind of like a smooth version of Metropolis. It depending on the ratio of the probabilities that you see between the moves, you accept with this particular probability. And the nice thing about these algorithms is that the modified Markov chain that you get after applying this rule in every step is that the stationary distribution is going to be proportional to this vector tau. And moreover, if this exploratory Markov chain had a unique stationary state, then also this stationary state tau will be the unique fixed point, and therefore, if you run this modified Markov chain for a long enough time, it will converge to that distribution. And the way to see that this is going to be the stationary distribution is that this Markov chain is detailed balanced, also known as reversible, with respect to this distribution tau, proportional to tau. And so what detailed balanced means is that if you look at any pair of configurations, then the transition, the probability mass along this transition is the same in both directions. So you are more likely to move from one configuration to the other because of these accept-reject rules, but you are also more likely or less likely to begin with to be in that configuration if you are in this target distribution. And these things just balance each other out. So if you happen to be already in the target distribution and then you make the move, then it has the same overall probability to move from Z to Z prime than from Z prime to Z. And of course, if that is the case, then there is the same probability mass exchange along every edge in this Markov chain, which means that it's a stationary distribution. So detailed balance is very useful because it very naturally ensures that your target distribution is the stable distribution and that you are converging to it if you run this Markov process for a long enough time. And here I should mention that even if you are working on experiments and you want to make a name in theory, maybe just keep working in experiments, because Metropolis is a man who was working in experiments, experimented with classical computers in the 50s when it was a hard-to-come-by asset. And it turns out that he, well, according to some recollections of the authors, different authors, Metropolis was only providing the runtime of his magnificent classical computer in 1953 when they wrote this paper. And actually, Edward Teller and Marshall Rosenbluth, who were working heavily on the hydrogen bomb, but wanted to do something maybe increase their legacy by some more peaceful applications. They and their wives worked on the theory and the programming of this, and Metropolis only gave the runtime. So if you manage to maybe create a 1,000-qubit fault-tolerant quantum computer, then you might get your name written in some quantum algorithm theory as well. All right. So the hope that this algorithm actually works in examples that you care about, and for many systems of interest, it works. And I describe you the discrete time version of this algorithm, but there is also a continuous time version that is very similar, and from quantum perspective, it's maybe a little bit more easy to handle. So in the continuous time case, you have also some symmetric generators, some exploratory process. And to think about this matrix L, the off-diagonal entries of L are the jump rates. How likely are you to jump from one configuration to another in an infinitesimal time step. And the diagonal entry is simply the sum of the off-diagonal entries with a minus sign, and it just tells you how likely are you to move away from this side, so it's a decay term. And such a matrix is called a Laplacian matrix and can be associated a weighted directed graph. And for the Metropolis dynamics, Metropolis algorithm is described as a discrete time algorithm, but you can also define the continuous time version, which is the same. You just modify these jump rates with the same rule as before. If you happen to jump to a more likely position, you stay there. If you happen to jump to a less likely configuration, then you only accept this move with this ratio of the likelihoods. And Glauber dynamics actually was first defined in a continuous time setting, and the same thing as before, just modify the jump rates with that particular prefactor. And once again, this generator generates a continuous time Markov chain now, which has the same nice properties, that the stationary distribution is proportional to the Tiger distribution you had, and it's unique if L already had the unique stationary distribution before modification, and this modified generator L tau is detailed balanced, reversible with respect to this target, and also often converges rapidly in physically motivated systems. Same story. Okay, now that we understood discrete and continuous time Markov chains and their Metropolis Glauber dynamics, it's time to look for the quantum version. So how do we construct a quantum Metropolis algorithm? And well, first of all, you need to change the objective function. We no longer work with distributions, but quantum states, because the energy is described by a Hamiltonian operator rather than a diagonal thing which was in the classical case. For example, we can take the transverse field Ising model, where again there is some nearest neighbor interaction, but a transverse field in the direction of the x operators every side. And now the goal would be to sample from the distribution. Actually, I will denote it by rho to say that it's a quantum state, and it's written as tau, so it's a typo, sorry. So rho is a quantum state, the Gibbs state exponential minus beta h. We want to sample from this quantum state. And once again, what would be the natural analog of the classical case? Well, it turned out that the easy case was when we had a symmetric exploratory process. Symmetric corresponds to self-adjoint in the language of quantum mechanics. So we would like to have some self-adjoint quantum process, for example, quantum channel, and start with that. We would like modify, and once again, a good example would be, for example, pick a random spin and flip it, maybe flip with a poly X or a poly Z, something like that, for a random site. And okay, now let's do a quantum Metropolis from these ingredients, and this is what Temme, Osborne, Folbrach, Paulin, and Verstraete proposed a bit more than 10 years ago. And they said that let's do the same thing. Let's do basically a random walk, but now on the energy eigenstates of my Hamiltonian. So suppose that I was in energy eigenstate psi, and if my process brings me to energy eigenstate psi prime, if the energy decreases, then it's a more likely state, than accept it. And if the energy actually goes up, it's a less likely state, then only then reject with this probability, and this is again the ratio of the probabilities if you look at the Gibbs state. So this is basically just a random walk on the eigenstate. So if you happen to diagonalize your Hamiltonian, then you get a diagonal operator, and it's the same story than the classical case. So it seems that we are done. And we have the properties as before. This Gibbs state will be the stationary state, and we hope that it will converge rapidly for physically motivated systems. But there are some problems with implementing this algorithm. The Metropolis algorithm was nice and very useful because it was very simple to implement in classical simulations. The problem is that in this recipe, we need to compute the energy of these eigenstates before and after the jumps. Well, we have a method for that, phase estimation, but it has some limitations on accuracy, which makes things very difficult, actually. And the other thing is that if you make a transition, you are at a new state, you can do phase estimation, you can learn the energy of your new state, but what happens if your Metropolis rule tells you to go back to the previous state? Well, this sounds like a quantum cloning issue. You were somewhere, you moved to a new place, and now you have to go back where you were before. But how do you go back when you no longer have access to that state where you were before? You cannot just make a copy of it because of quantum no cloning. And they had some fix for it, but it was a complicated Marriott-Watrous rewinding strategy, which was also not very appealing from a practical perspective. Anyway, so there is a quantum Metropolis sampling proposed, but the key issue is this ambiguity and uncertainty in the energy estimation that arises. And the original solution used this Metropolis rewinding and some technically involved shift invariant boosted phase estimation, which in the form they uses it and need it in their analysis doesn't exist, unfortunately. And while there are other approaches that came up afterwards that just, for example, ignore this problem, which is of course unphysical, then there was a bit of a break in this line of research because this seemed to be a very tough problem to really fix. But there was some very nice progress by Wojcian and Teme a few years ago. And they looked at this continuous time variant of the Metropolis algorithm, which solved some nice things, nice difficulties, but they still had this issue with phase estimation, and they had to assume some periodic gaps in the spectrum to make their algorithm really work. And then follow-up work removed this unphysical assumption by saying that they randomly shifted the mesh of energy estimation that they had underlying, and that most likely worked out, but this random shifting is also a difficult procedure and introduced large overheads, and was very difficult to analyze what's happening there. And so we think we have an easier solution that actually Anthony will talk a bit more about. And this was to apply some smoothened versions of phase estimation with some damped phase estimation that we called operator Fourier transform, and Anthony will talk a little bit about it. And what I want to talk about today is a new construction that we recently came up with, and independently a group at Berkeley by 3 people, Ding, Lee, and Lin, also came up with a very similar construction independently. And so this construction says that don't do phase estimation, simply reweigh jumps in a coherent fashion and implement this in a quantum computer as a weighted integral over Heisenberg evolution for not too long times. So this is implementable and also conceptually interesting, a smooth variant of the previous attempts. Okay, and to explain the new construction and how it relates to earlier constructions and other quantum mechanical frameworks, it's useful to look at continuous time quantum evolution in a dissipative system, also known as continuous time quantum Markov chains. And their generator, the classical case for continuous time Markov chains was a Laplacian, and here it becomes a Lindbladian. And the infinitesimal generator of such continuous time Markov dynamics is like this. First of all, it has a transition part, which is a completely positive, abbreviated as CP map, that is describing the jumps. And then you have your decay term, which tells you that if you are transitioning from a place to another one, then you are going to be absent where you were before. So this is the term that is required for making this procedure trace preserving. This is the decay term. And because it's quantum, you have the additional freedom to induce some coherent evolution on top of this more probabilistic jump version. And that's a coherent term which has some Hermitian operator that describes this coherent evolution. So this is a very general way to describe quantum evolution. For example, if you have no jumps, then it just becomes time-independent Hamiltonian simulation this way. Of course, you can make things time-dependent, but I'm not going to in that direction in this talk. Okay, so this is a Lindbladian, and so this is the right language to talk about quantum generalizations of Glauber and Metropolis dynamics. From this generator, which is a super operator, so this is a super operator that acts on density operators, you get the induced quantum channel after exponentiating this linear super operator. And this is your actual quantum process that happens, and it depends continuously on time. The nice thing, if you are looking for a quantum generalization of Metropolis in this language, is that there is no reject step. It's just a continuous time evolution, and that saves you the difficulty of doing this cloning, Marriott, Vetrus, all these other difficulties, because everything happens continuously. There is no discrete rejection happening in this picture. That's one nice advantage of it. And this object is studied in open quantum systems, and their thermalization is often described using this so-called Davis generator. And I am describing here a Metropolis rule version of Davis generator. There is some freedom in the choice of parameters, but to connect to this Metropolis algorithm, I'm going to describe this. I called it Davis Metropolis generator because it's the Davis generator, but in the Metropolis version of it. Okay, so suppose that you have a Hamiltonian, and for simplicity in the talk, I assume that there are no degeneracies in any way. That can be also handled, but it's just easier to write formulas if you don't have degeneracies. Okay, so what it does is that you had your jump operators in the Lindbladian, these KJ operators, and it says that, okay, look at the jump operator and just look at every different energy transition, that is this psi prime KJ psi terms, and isolate them and reduce, make a new jump operator for every different energy transition, and then reduce this transition weight according to the Metropolis rule. So now this bottom line is actually describing the continuous time version of the quantum Metropolis algorithm I told you like 2 slides ago. It is just the continuous time version of that. Now the issue is that it really distinguishes all different energy eigenstates. And that's a problem because you have exponentially many energy eigenstates. The best way to distinguish them is by label them by energy or something like that. But it would mean that to implement such an operator, you would need to resolve energies to an exponentially small amount, which would mean an exponential amount of exponential time required for phase estimation. So this is really a problematic operator. You have not much chance to implement this exactly in a quantum computer, and various ways were proposed to fix this. Now, I am going to tell you our fix in a general, but fitting in a general scheme. So what we ultimately want to do, I'm rewriting first the Lindbladian in a more compact term. I'm saying that Lindbladian has a transition part, which is a CP map, a decay term, which is just very easily depends on, it is directly given by the transition part, and then there is a coherent term, which is a freedom in principle. It can be anything unrelated to the transition part. So this is the process that I have. For example, this exploratory process that I described before. And now we wish to create a new process where I have a target Gibbs state rho. I want to sample from this target Gibbs state, and I want to modify my map accordingly. So I need to modify the transition part. The decay term is given by that immediately. I don't need to pay special attention to that. And there is a coherent term. Well, it's independent. Let's see what we can do about this. One of the insights in this one of the earlier Gibbs sampling paper with Anthony and Michael was that as long as you manage to make the transition part such that it's detailed balanced, it really fixes the Gibbs state, then the coherent term is uniquely determined. So it means that once you figured out how to make a detailed balanced transitions, then there is a single coherent term that you should choose, and there is a fixed recipe which is also efficiently implementable, so you don't need to worry too much about it. The whole problem reduces to making the transitions detailed balanced. That's the only thing you need to solve, and all the other things are deterministic. You don't need to worry about them later. And this whole thing works especially nice when you have a self-adjoint transition part. For example, if you have jump operators that are self-adjoint themselves, that is sufficient. For example, if you have some poly transitions on some sites, that's automatically going to be a self-adjoint transition map. So you can think about the transition part as applying a random poly at a random site. That's a very practical choice. Sometimes it's useful to add different jump operators, like a few site polys. That also fits in this definition. Think about the transition part like this: a few site poly operator randomly chosen. Okay, so we have these few site polys, and we would like to jump with them, but we need to modify them so that they become detail balanced with respect to the Gibbs state that I have in mind. So the constructions that we describe actually all turn out to be linear, so they depend linearly in this transition part of the map, and that's very useful because it means that you can analyze the construction on the level of Krauss operators, the Krauss operators of the transition part. And you know, otherwise it would be difficult because the Krauss operators are not uniquely determined by the map. You have freedom of choice, but if it's linear, then it doesn't matter which decomposition you take. So linearity is very useful for several reasons. For example, the ambiguity in Krauss operators is resolved by it. All right. So the Davis Metropolis rule in this case, even if you have a single Krauss operator, it's a very simple channel, it will decompose it to up to n square operators, n square Krauss operators. So you started with a single Krauss operator, the simplest possible channel in this sense, and you had an n-dimensional space, and suddenly you have n square Krauss operators, which is the maximal number of Krauss operators of any CP map. So you go from the simplest to the most difficult, most general case in one go. That's not very useful. And so this new construction that I describe is a smooth, the construction that Anthony will talk about is a smoothened version of this. Still has this issue that creates lots of Krauss operators. But the new construction is preserving the number of Krauss operators. It just operates on the elements, matrix elements of this Krauss operator. So a single Krauss operator is mapped to a single Krauss operator, and therefore the number of jumps do not increase. So what it says, a similar weighing factor as before appears, but with a square root, because with the Krauss operator you act both from left and right, and so the square root naturally gets squared and gets the same weighing factor as before. But now what you do is you take your Krauss operator, and the modified Krauss operator will have matrix elements that are reweighed with these things, with this prefactor. But still, a single Krauss operator will be mapped to a simple new Krauss operator. Okay, now here is this rule. Okay, how do you do it? Of course, you can just diagonalize your Hamilton operator, write your Krauss operator, which is, for example, a single poly jump, in the eigenbasis of the Hamiltonian, just write this prefactor everywhere and you are done. Very quantum computer friendly, right? Not really. However, if you look at the Fourier transformation of this thing, it turns out that you can write this thing in time domain, and it can be represented as an integral over Heisenberg evolution, which is on the next slide, but what I wanted to say in this slide, yeah. Okay, one other nice property of this construction that it almost surely preserves the uniqueness of the fixed point. It's a very mathematical statement. If the exploratory process you had a unique fixed point, then most likely you will have a unique fixed point also after you apply this rule. Okay, so this is how you would implement, this is a quantum computer implementation friendly way, a rewriting of the previous rule. It just says that if you do some Fourier transform and computations, then you will find a nice and relatively smooth function f, which is a weighing function. And you need to Heisenberg evolve your jump operator k and weigh the different times with different weights and integrate over. And now this gives you the new operator. Now it turns out that in this representation, this version, the Metropolis rule is a bit less nice than the resulting f function. The weighing function is a bit ugly. But the Glauber version, which is more smooth and more physically motivated, actually is very nice. And the key property is that this weighing function f is exponentially decaying for times larger than beta. And you can truncate the integral. So basically, you need to only do Heisenberg evolution up to time beta, and then do some weighing. For example, in a quantum algorithmic language, just do some LCU. And I see that Nathan arrived at the right moment because LCU appeared at this point in the talk. It makes a very efficient implementation for it. And another thing that this integral representation tells you is that you can apply Lieb-Robinson bounds. You have only about beta time Heisenberg evolution, which means that if your jump operator was, for example, single-side Pauli, and you have a local Hamiltonian operator, then the new jump operator will be also local. The locality spreads. So depending on beta, you will have a single-side operator may act on a beta neighborhood of the original action, but not further than that. So we cannot fully save the nice property of the Metropolis algorithm that a local update is transformed to a new local update rule, but at least roughly preserves it up to and this is probably the best you can hope in the non-commutative scenario. If you have a local update rule, a local Pauli jump, it will get mapped to a quasi-local jump operator. And you do it for all the jumps that you have. And so this describes the rule. And okay, at this point, it defines your new jump operators, and then you can apply your favorite Lindbladian simulation algorithm. Now the question, do you have a favorite Lindbladian simulation algorithm? Probably not. The problem is that unlike for Hamiltonian simulation, where you have first-order trotter, second-order trotter, and all these are kind of nice, actually going beyond first order in Lindbladian simulation is very difficult. First order is roughly okay, but then you have the bad scaling of t squared over epsilon. And there are logarithmic, they are like high-order formulas or infinitely high order that logarithmically depend on epsilon, but those are really complicated algorithms, like really complicated. And so that's probably not your favorite Lindbladian simulation algorithm. So the best part is no part, meaning the best Lindbladian simulation algorithm is when you don't have Lindbladian simulation algorithm. And that is why we wanted a discrete time construction, which overcomes this difficulty. And although we were thinking about these algorithms in the continuous time setting, we now can convert it back to a discrete time quantum Markov chain, which is a quantum channel. Okay, and how would this go? So the idea is that we have constructed a transition part, a CP map, which is detailed balanced. And actually, what we showed is that there is a unique and natural complementary Krauss operator, such that if you take the CP map, which is the transition part that you constructed, and add the single Krauss operator, Now this becomes Rho detailed balanced quantum channel. So to make it a quantum channel, it has to be trace preserving. So you restore the trace preserving property and you keep the detailed balanced condition alive. And this is the new thing that we show is possible. If you have access to all these Krauss operators, then with standard techniques such as oblivious amplification, which I'm sure that everyone is fully aware of and eats it for breakfast. Anyway, this is not a super complicated technique, but you can actually implement the effect of the quantum channel using such relatively standard quantum techniques.
Is it unitary?
So this is not a unitary channel, but the Stein spring dilation, is it called Stein spring dilation for states? Anyway, so you can implement the dilation of the channel, which is a unitary, or at least an isometry, and apply oblivious amplification for that. Yeah. All right. So in brief, if you are not familiar with this technique, oblivious amplification says that if you have a quantum operation that preserves the norm of your quantum state, then you can amplify it without having to know what was this initial quantum state to begin with. And that's very good when you want to compose an algorithm, like apply your algorithm over and over. In standard amplification, you would have to go back to the beginning every time and exponential complexity kicks in. Versus here, because the norm doesn't change, somehow you can work around it and there is no need to go back. Very useful, and it's basically says that if you have a quantum channel which is trace preserving, then it's norm preserving in the dilation sense, and then you can apply this trick. Okay, and now here is a wonderful formula for this Krauss operator. It is just this ugly square root of exponentially complicated quantum object, so it's surely nicely implementable. Well, maybe you don't see from this because, yeah, this Rho is really a ill-behaved object, but actually we found a very nice Taylor expansion of this Krauss operator. And using this Taylor series expansion, we can analyze it, and it turns out that there is some shortcut where you can, with some clever divide and conquer strategy, you can actually implement it using some quantum linear algebra techniques. And this alternative representation gives you a nice implementation via quantum singularity transformation and block encoding techniques. And well, it remains to be seen whether it's really beating the Lindblad simulation method, because it's also some difficulties, but we are hopeful that it can be practical when you have a 1,000-qubit error-corrected quantum computer, hopefully. Let me know if you have. Okay. So now I arrive to the open question section. So the main open question is to see and verify that this algorithm and this family of algorithms, it's a rapid way of developing, of preparing quantum states. So the issue is that although we can prove often uniqueness of the fixed point, so that if you run this algorithm for a long enough time, you will get to the Gibbs state. Now, how long is that time? This is something that has to be examined on a case-by-case cases. There is some nice theoretical results already. It has been shown that for high enough temperature, it indeed converges rapidly. Of course, you want to care about low enough temperatures, and this is the big question to tackle for different systems. And yeah, so basically this is a different way of stating this question, that bounding this mixing time or related quantity, which is the gap of the Lindbladian. And because it's basically modeling a dissipative preparation of quantum states, we expect that it should have some level of noise resistance, because if you introduce some small mistake, by dissipation it should disappear. That's the hope. And to what level it actually holds up, that's also an interesting theory question. And probably the most interesting aspect, that finally we maybe have a quadratic improvement for quantum capture. Thank you.
Okay, thank you. So we have time for a few questions, maybe.
Hi. About the bounding the mixing time, have you thought of any like quantum generalizations for like isoperimetric type inequalities here, like Cheeger bounds or something? Can you think about it in this context?
I am not super familiar if those techniques have been applied in this case of quantum channels, these isomer perimetric equalities. I haven't looked into them, but maybe I should.
Yeah, because I guess the classical limit will just give you Glauber or Metropolis, and there it is like useful. So there should be.
Yeah, in classical systems, they do this kind of analysis. I'm not sure if this construction with coherent reweighings and all the other things, it supports that, but maybe.
Thank you.
Olas, you have a question?
Hey, thank you. Does it work? Yeah, hear me. Thank you very much for a nice talk. Just a very quick question. When you specified about coherent part, you said that it uniquely defined by the map T, right?
Yes.
But my question is simple. For example, if I imagine that I have Gibbs state, I know that adding Hamiltonian shouldn't make my Gibbs state change, right? So what if I add Hamiltonian to C? Does it break dynamics? It doesn't make. And if it doesn't, then why is it unique? If I add just Hamiltonian evolution on top of this, like thermal.
Yeah. So I just you say, isn't there a freedom in adding multiples of your system Hamiltonian? I think it's. I think that freedom is not present actually, because it will do different. It will add different phases to different parts of the eigenstate. Of course, if you just have that Hamiltonian evolution for a Gibbs state, that doesn't ruin things. But okay, so here it's kind of a stronger condition than that. So we don't just ask that it doesn't do anything to the Gibbs state, but also the transitions between the Gibbs state and other states is in balance. And adding the system Hamiltonian could ruin that part. So it's a stronger condition than just fixing, not doing anything to the Gibbs state.
So then I can only think about this as
maybe,
a nice way to prepare.
Maybe let's take this in the lunch break.
Do you hear me now?
Yeah, I think we should move on to the next talk. There's going to be a related
happy to
talk
discuss this afterwards.
in the afternoon session, so I think there's many more opportunities to discuss this. So let's thank András again.